Okay. So today we'll continue with various applications of the technique we developed, and the first part will be classification of one-dimensional algebraic groups. And the answer is known to everybody. So it's either the additive group or the multiplicative group or an elliptic curve. Okay, and then in the end we will prove that they are all distinct. I mean, certainly the affine line is just as a variety different from the multiplicative group and from an elliptic curve, but then the elliptic curves also have some moduli, so there are different elliptic curves. But the point is that if two varieties are the same, then the group structure is also the same. So on a given curve, there is at most one structure of algebraic group. I mean, after you fix the unit, the neutral element. Okay, so let's prove this. This classification theory, and we start with the evident observation, but crucial, that the cotangent bundle, the canonical class omega G, is trivial. And this is because the or the normal bundle to the diagonal delta in the square of our group is trivial. If you remember, we when we just introduced the differentials, maybe the first class this year in January, we computed the differential of the vector space. Yeah, there is additive commutative group of the vector space, and we computed the sheaf of Kähler differentials explicitly. It was trivial, certainly, and to this end, we just decomposed V times V as the diagonal delta V times, say, the first copy. Okay, it is the same V, just two copies, and this was true. It works for the same price here. I mean, G times G is isomorphic. Well, again, the first copy and the second copy is isomorphic to the diagonal times, say, the first copy. And it implies that the normal bundle to the diagonal is trivial. Okay, fine. And somehow this is the crucial point, because it means that if G is projective, then necessarily the genus of G is 1, right? Because the degree of the canonical class, the dualizing invertible sheaf, is 2G minus 2. Okay, so the genus is 1, and so G is elliptic. Fine. Now, if G is not projective, we consider its compactification.
Как определяется эта компактификация?
Compactification. Yeah, I'm being well. I'm loosely speaking, it's a compactification, but rigorously, this is the unique projective smooth curve containing our open group.
А почему такая существует?
Well, maybe a month or more ago, we classified all curves in a sense. Yeah, in particular, this is clear from this classification. So in any birational class, there exists a unique projective smooth curve. Okay. Fine. Now let's apply this extension through divisor theorem we proved last time. And let's prove that we have a birational morphism. Well, sorry, a rational morphism. Say mu from G times G bar to G bar. I mean, G bar is birational to G. So when I say birational morphism, I mean just multiplication morphism from G times G to G. But we view it as a birational morphism of action of G on G bar. So this rational morphism is actually regular. Okay, so let's prove this. And immediately follows from the extension through divisor. So by the extension through divisors theorem, the maximal open subset U in G times G bar of regularity has complement of codimension at least 2.
Если такого не существует?
Well, we discussed this last time. Yeah, I'm just quoting literally the theorem we proved last time. So just look it up. So it has a complement of codimension at least 2. This means that the complement is finite. G times G bar minus U is finite. Okay, it's finite and certainly contained in G times the boundary, right? Because on G times G, this is the usual multiplication. So let say H and G bar in this boundary be a point in the complement. We want to prove that it's empty, right? And suppose there it is not empty, there is a point there. And then note that we can just shift this point away, so to say. I mean that the multiplication of H and G bar is the same as multiplication of H times G and G inverse times G bar for any element of the group. Okay, just by definition. Fine. So we can, since there were only finitely many bad points and the group is infinite, we can find such G that moves our point away from this bad finite set. So G is infinite and this bad set is finite. Hence, there is G such that H times G and G inverse times G bar lies in U. Okay, and so we can so to say redefine mu so that it is regular at this suspicious point H G bar. Okay, so we proved that it is defined everywhere. This was the proof of this lemma, that this rational multiplication morphism is actually a regular multiplication morphism. And now let's use that it is regular. By the way, note that under this multiplication morphism, mu, G times G bar goes to G bar. If you take the boundary mu of G times D G, I mean the boundary G bar minus G certainly lies in the boundary. Okay, so the action of our group preserves the boundary, and since the boundary is finite, it means that any point of the boundary is preserved. Yeah, by the way, maybe from the very beginning, I should say that we're talking about connected groups, because otherwise certainly can multiply with any finite group, and you will get many more one-dimensional groups. Sorry.
Для чего нам компактификация потребовалась?
Well, because we already argued that if our group was projective from the very start, then it has genus 1, right? Now I will argue that if it's not projective, its compactification has genus 0. And in order to talk about genus, you need compact curves. So that's why we used compactification. Okay.
Is G bar a group itself?
Certainly not, because just what are we talking about? It's either elliptic or additive or multiplicative. For additive or multiplicative, it will be just P1, projective line, right? Certainly projective line is not a group just because its tangent bundle is not trivial, right?
Okay.
So, certainly not. Okay, so the boundary is finite, the group is connected, so it means that the action of G preserves any point of the boundary. That preserves it pointwise. And then now choose a non-zero tangent vector V at the origin, so to say. Well, let me call it E. We have a tangent space at the neutral element at the unit of our group. We take this non-zero tangent vector and, so to say, spread it all over G bar. So what does it mean? We have this multiplication morphism from G times G bar to G bar, and now we're restricted to just the identity element E times G bar to G bar, and they take the differential D of this map. Okay, then it takes the differential d mu takes our vector v at identity plus zero vector at another element. Okay, and this gives you some vector field on G bar. Okay, d mu of v plus 0 is a vector field on G bar. Well, it's, so to say, constant at G, because we know that the tangent bundle is trivial. And in this sense, it's constant. Its value is v everywhere. Okay, but vanishing at the boundary, since the boundary is fixed by any translation. Fixes any point of the boundary. Okay, and so we produced a regular vector field, right? And this means, well, it's enough. So we produced a non-zero section of the tangent bundle of G bar, and this is just the canonical class of G bar inverse. Okay, so it means that the degree of the canonical class of G bar is well, at least 0, but the inverse canonical bundle is non-negative, and so the degree of the canonical bundle is non-positive. So it means that the genus of G bar is either 0 or 1. But if it is 1, we already well, you see, if the boundary is non-trivial, then our vector field is vanishing somewhere, so the degree is strictly positive. degree of the canonical class inverse is strictly positive, and hence genus of G bar is just 0. And in particular, the degree of this tangent bundle is 2. And so it means that the boundary where the vector field vanishes has either 2 points or 1 point.
А это откуда следует?
Because this is how many our vector field vanishes, how many times our vector field vanishes. So it can either vanish at 1 point with multiplicity 2, our vector field vanishes with multiplicity 2, or there are 2 points and our vector field vanishes at both points
Спасибо.
with multiplicity 1. Okay, so in this case, it will be the additive group inside P1, and in this case, it will be well, I don't have any place left. Sorry. So in this case, it will be the multiplicative group inside P1. That is the compactification. Okay, so as a variety, as an affine algebraic variety, our group is identified at this point, and we only have to identify the multiplication law. Mu from G times G to G. Okay, so let's first consider the case when G is the additive group. So it's just the affine line so far. And then mu is just morphism from A1 times A1 to A1. So it's given just by some function. So mu is just a function, but let's call it f, because we usually denote functions this way. So what do we know about this function? First, we know that f of x. Yeah, we also have to fix the neutral element, and let's do this. Fix, say, the point 0 as the neutral element. So now we want to prove that f of xy is just x plus y. Okay, there are no other choices. Let's prove this. What do we know? At least we know that f of x times 0 is x. We know that f of 0 and y is y, right? Because this 0 is the neutral element. And also we know that for any fixed point x in our group, the group law f of x and y is well, as a map from the second copy of A1 to A1 is an isomorphism. Sorry. But then it means that f of x, well, maybe let's call it x naught, f of x naught and y is a linear map. Okay. I don't know how to say it. A of x naught y plus b of x naught. Oops, sorry. What did I do? Pardon me. What was the question?
Почему f линейно?
Why is it linear? Because you need a polynomial. This function is a polynomial in y, right? And you know that this polynomial gives an isomorphism from A1 to A1, right?
Да.
F of x0 and y is an isomorphism from A1 to A1. And it's a polynomial. But just think about it for a moment. Polynomial that is an isomorphism. I mean, it has a unique root, for example. Yeah. So it's of degree 1, right?
Параболу можно же отобразить y1? Наверное, ну.
Once again, it's a polynomial in one variable. And this polynomial in one variable has a unique preimage of any point. The preimage of any point is just one point. Yeah, so it has degree 1. Otherwise, the preimage of any point would be of cardinality degree of this polynomial.
Спасибо.
Right? Welcome. And also, you know that from the very first line, f of x0 is x, f of 0 y is y, so it means that it actually equals a of x naught times y, and then symmetrically sorry, what am I saying? No, I'm saying something stupid. It's not this. It's rather y. Sorry. It's y. Sorry. It's y plus b of x naught, vice versa. Symmetrically, f of x and y naught is x plus whatever c of y naught, and
От x0 пропала единица.
pardon me?
Почему от
Again?
x0 стала единицей?
I cannot quite hear you.
Почему от x0 стала единицей?
Just because we know that f of 0y is y.
Ну, понял, спасибо.
And so it means that f of xy is just x plus y. Fine. So we consider the case of additive group. Now the case of multiplicative group. Yeah. So now G is GM, and again we place the neutral element at 1. And again, we have the multiplication from GM times GM. This is just the puncture-defined line. To the puncture-defined line is given by some function f. But now this function f of xy is a Laurent polynomial. And in x and y, but it never vanishes. Right, because it lands into the puncture-defined line, and then just similarly, you see maybe let me say that it uses the following fact that any nowhere vanishing function on the puncture-defined line is necessarily some constant times some power of the coordinate. Okay, it's polynomial, but this polynomial must have no roots away from the origin, so it must be just monomial, just like this. So the similar argument proves that f of xy is just the product.
Почему кроме нуля не имеет других корней?
So the function f must land into the puncture-defined line, so it must have no zeros. Yeah, it cannot assume value 0 by the definition. Okay, so it never vanishes. So there are no roots. But since we consider the punctured line, there may be some roots at 0. Okay, but away from 0, no roots at all. Okay.
Понял, спасибо.
Welcome. So this is it. This theorem is proved. And now let us.
В каком месте мы использовали лемму?
Where did we use this lemma? Yeah.
Yeah.
Right. Because we used it to construct this vector field. Yeah. At the next page. Right. Maybe yeah. At the third page, we constructed this vector field that was regular everywhere and vanished at the boundary. So the point is, on the curves of higher genus, the canonical class is positive, but the inverse invertible sheaf, the tangent bundle is negative, so it cannot have any sections at all. But in the group case, the tangent bundle must have some sections, and moreover, they must vanish at infinity. So there are many sections. And it can only happen if the genus is 0. That was the key point of the argument. Welcome. So now the uniqueness for elliptic curves. So given an elliptic curve E with a point say 0 with a marked point, say E. There is a unique multiplication law E times E to E with the neutral element so we already know that there is one. We proved it. You proved it in your home assignment, and then we proved it from some more scientific point of view. And now the question is about uniqueness, so that we don't have any choice. Okay. So the proof is in a sense very similar to what we did. We know that the restriction of mu onto E times E is just the identity, and also the restriction of mu on the other fiber is also the identity. And now we use the following rigidity dilemma. Due to David Mumford. That is an extremely useful tool. So it's much more important than this application about elliptic curves. Elliptic curves are very nice and beautiful, but this rigidity dilemma is very general and very much useful. So you will encounter it many times in many applications. So we have a morphism from the product of two varieties to another one. So X is irreducible and projective. Then Y is also irreducible. And Z is separable. And for theory irreducible, as you will see. And we have a morphism F from X times Y into Z. And suppose this morphism contracts one fiber. That's the whole fiber. So F of X times Y naught is just 1 point. And then this morphism just factors through the projection to Y. We have X times Y. Then there is projection to Y. And then there is some morphism, say G to Z. So in other words, if it contracts one fiber, then it contracts all the fibers. Okay, this is the very useful rigidity result of Mumford. So let's prove this. And the proof is surprisingly simple. So take an affine neighborhood W of this of the image of contracted fiber. So it lies in Z and contains f of x times y naught, this contracted fiber. Okay, and then take the complement, the projection to y of the product without the preimage of this open neighborhood. So the preimage of open neighborhood is open. So the complement is closed, but now x was assumed to be projective, or maybe proper. So the projection of this closed subset to y is also closed. Let's call it f. It's closed. And x was projective. Okay, and now let's take the complementary open. It's open neighborhood of our point y0, and take any y in this neighborhood, and then if we take the corresponding fiber, x times y, then it lands into W. But W is affine, and x times y is projective. So the image must be 1 point. Okay, so we see that set theoretically, f restricted to x times this open set V does factor through projection to y. That's what I wanted to prove. Only we wanna know that the remaining part, like G, is actually a morphism. Yeah, there is some set theoretic map G, but I want to prove that it's an algebraic morphism. So there is.
Я пропустил, а как определяется G?
Well, we know that all the fibers are contracted, right? So the value of f only depends on point y. It does not depend on your point in x. That's what we just proved. It's a theoretic map G from V to Z, such that f restricted to x times V is the composition of G and a projection to y. And now I have to check that G is an algebraic morphism. But this is immediate because G is just f restricted to to any point x naught times v, right? Just by the very construction. Fine, so prove this, but only in the open subset. So proved everything. For f restricted to v, but our y was irreducible, and we started from any point. So any point has such a neighborhood. Y is irreducible. Any point such a neighborhood, and so well, G is f restricted to x naught times the whole of y. Fine. So this famous Mumford theorem is proved, and now let's apply it to our elliptic business. Well, let's have two multiplication laws. Yeah. Suppose we have mu1 and mu2 from e times e to e, but they share the same neutral element. So mu I restricted to e times e is the identity of e, and the same as mu I restricted to e times e. So we're going to prove that mu1 is equal to mu2, and we just apply the Mumford rigidity. To the morphism pi from e times e to e. So this was x, this was y, this was z, and this morphism pi of e1, e2 is equal to mu2 of e1, e2, mu1 of e1, e2. Sorry. Yeah. mu1 inverse. In the sense of this inverse is taken in the sense of doesn't matter what, in fact. No, let's say in the sense of mu2. Okay. Then we know that pi of 0 and e2 is 0. Sorry, it's not sorry. We denoted it not 0 but e. Pi of e and e2.
Это мы определили так пи отображение.
Yes, that's just the definition. So pi of e, that was the, we assume that e is the neutral element for both multiplication laws. So this is e, and there's also pi of e1 and e, and hence it follows that pi of e1, e2 is identically e, and we are done. Okay. By the way, David Mumford is alive and well. Well, he is pretty old, 80 something years old, but still working. Okay, so now let's start something absolutely new, new topic, namely correspondences for curves. Well, on the one hand, we will use the techniques we developed so far. On the other hand, by itself, this theory is, well, has many very useful applications. Already next week, we will prove the famous Andreev conjectures on the number of solutions of well, in general, Andreev conjectures, they give very sharp estimates for the number of solutions of polynomial equations over finite fields. I mean, you write down some equations, say 5 equations in 7 variables, say the coefficients of these equations are in finite field FQ, and then you just count number of solutions over FQ. Maybe there are no solutions at all, but then you extend your base field FQ, say FQ squared, and you count the number of solutions over FQ squared, or this bigger field. Again, there might be no solutions whatsoever. Then you count the solutions over FQ cubed, and then you take the degree higher and higher, FQ to the power n, and if you take this in the limit, you will obtain the algebraic closure of FQ, and over this algebraically closed field, you will have many solutions. So eventually, you will start getting more and more solutions over the finite extensions of your finite field FQ. And the question is how the number of solutions grows as the degree of your extension grows. Well, certainly depends on your equations, on the initial equations, but this dependence is very rough, so to say. So you can say a lot about this growth rate, well, independently of the particular equations. And this is a very big theory that initiated from some conjectures of Andreev and was developed by Grothendieck. In a sense, most interest of Grothendieck in algebraic geometry was sparked by these conjectures by Andreev. And then 50 years ago, the last step was taken by Pierre Deligne. So he proved the last of Andreev conjectures, Riemann hypothesis. But the whole business started with Andreev proving this for curves. So when those equations over algebraic closure of finite field define a curve, a projective curve, then this result was proved by Andreev himself, like 80 years ago. And this we will study next week. As an application of this theory, we start studying today. Okay? But in fact, this theory again has many more applications, not only to wave conjectures, and it was developed not just for wave conjectures. And in a sense, this approach to wave conjectures is the ideal, the best one. Unfortunately, it does not work in higher dimensions. It works only for curves. And the approach is somewhat motivic. And the word is due to Grothendieck, and this was his well, his favorite dream, to develop this theory of motifs. But unfortunately, it is in the way envisioned by Grothendieck, it is still non-existent. there were some very important successes in this theory due to Voevodsky and many others, but somehow not in the original way Grothendieck envisioned it 60 years ago. So in this ideal way, it only works for curves, and that's what we're starting to do now. So somehow the basic idea is to use some topological methods. Say in topology, maybe you heard about the Lefschetz fixed point formula. It is some estimate on the number of fixed points of some endomorphism of an algebraic variety in terms of its action on cohomology. Just singular cohomology, topological Betti cohomology. Well, eventually Grothendieck and his school was able to develop this parallel theory over finite field. So there is no notion of singular cohomology for algebraic varieties over finite field, but Grothendieck developed the notion of étale cohomology, and it was a perfect substitute, and it worked just as desired. And using this Lefschetz fixed point formula approach, he was able to prove the Weil conjectures. But for example, the coefficients of this cohomology theory, they are necessarily not real numbers. They must be some p-adic numbers, and this p must be prime to q. So we started from some finite field fq, and the coefficients of this étale cohomology theory must be some other prime, necessarily some other prime, and necessarily some prime. So it's p-adic cohomology or some other p, and it's never real or integral. For some deep arithmetical reasons, there is no possibility to develop a cohomology theory with real coefficients or with rational coefficients or with integral coefficients. It's out of question. It just cannot possibly be so.
Извините, а вот второй подход не Grothendieck, он на основе чего разрабатывал?
Well, we'll just start doing this right away. You will see how it works. But the key difference is that in this other approach, the coefficients are just integers, and it uses in the most crucial way some positivity. So I hope I will be able to formulate this positivity in a few minutes, and then we'll prove it next time. And unfortunately, in the Grothendieck approach to Weil conjectures, there is no positivity. Well, there are standard conjectures due to Grothendieck about this positivity, but they're only conjectures. They're not proved. The way that the actual proof works up to date is it is some other way, without any use of positivity. Okay, but for curves, there is such an argument, and we're starting to develop this argument for curve. Okay, so what are the correspondence? We just have two curves, P and S, smooth projective curves. And a correspondence is another curve, say X, that maps to both of them in a finite way. PC, PS, they're both finite. So well, historically, like C and S, the moduli spaces, they are curved, but they are defined as moduli spaces of elliptic curves. With some extra structure that is called rigidity. So elliptic curve is a group, as we just seen, you may consider torsion points of this group, like 3 torsion. Yeah, there's some group of order 9, and rigidity is a fixed identification of this torsion group with z mod 3 times z mod 3, for example, or something of the sort. Then X is the so-called Heike correspondence. So roughly, it says that C is isogenous to S. That is, we have a finite homomorphism. The Sordatic homomorphism C to S. Okay, and there are many such homomorphisms in principle. So there may be many curves T that are isogenous to S, and many curves S isogenous to C. So in other words, this X is a sort of multi-valued morphism. Well, maybe X is the graph of a multi-valued morphism. Okay, so if projection from X to C, for example, is an isomorphism 1-to-1, then certainly X is the graph of some morphism induced from C to F, or vice versa, in the opposite direction. But in general, if the degree of PC is bigger than 1 and the degree of PS is also bigger than 1, then roughly speaking, X is the graph of a multi-valued morphism. And there's a standard terminology, at least when I went to high school, we were taught exactly the language of correspondences in the textbook by Kolmogorov. Okay, so these are correspondences, and now we take some more abstract point of view. Well, we certainly obtain the morphism PC and PS from X to the product C times S, and we may restrict ourselves to the correspondences such that X embeds into C times S, and so X is say a smooth, well, it's not necessary, divisor, and then we can consider the invertible sheaf. O C times S of X. Okay, and now from this we arrive at the standard terminology to be used from now on. So I don't know the working definition. A correspondence is an invertible sheaf L on the product C times S. Okay. So this is how we will use this term from now on. Although, as we've just seen, there are various other uses of this term, but for the next week, we will for this and the next week, we'll just have this definition, and thus the class of this correspondence lies in pcar of the product surface, and there is some equivalence relation, because in this pcar group we have a subgroup, just pcar of C times pcar of S, right? Because we just can pull back the invertible sheaves from C and from S. This and we will be interested in the quotient group. So let's call it bar of C times S is the pcar group of this surface modulo the line bundles lifted from the factors.
А почему мы отфакторизовываем такое вот произведение Декарта?
Well, you will see. Well, somehow maybe it is useful to realize that there is a first term class. Well, if our field K is complex numbers, then the first term class C1, the homomorphism from the pcar group of anything at all, say X. Well, X maybe was used in the previous page. Let's call Y to the second cohomology group, just Betty singular cohomology of Y with coefficients in Z, but also it goes to so-called 1-1 part of the Hodge structure of Y with complex coefficients. Okay, and so when Y is the product of these two curves, the surface that splits into the product, then this quotient for the pcar goes into the subspace or with sublattice of this cohomology, where certain bilinear form is positive definite. And that's very important. That's what we'll use. But this bilinear form can be defined without going to cohomology. It can be defined in the inner terms of Picard, and that's what we'll do. So it will work not necessarily topologically over complex numbers, but over arbitrary field. Okay, this positivity is called Riemann bilinear relation over complex numbers, but we will prove this positivity over arbitrary field. Over any k without resorting to topology in algebraic terms of this Picard quotient group. Okay, so while I have a few minutes, let me define some bilinear form that will turn out to be positive. So first we define the C and S degrees of line bundles. And let's take this line bundle and restrict it to any fiber, like say C times S for any point in the first factor. And then we know that the Euler characteristic, of S with coefficients in this is independent of the fiber. Of the choice of this point, since L is flat over C. Okay. So you have this line bundle over the product, but when you restrict to fibers, you obtain the varying family of line bundles over S, depending on the point of C. And the other characteristic of any such line bundle is the same. It does not depend on the choice of your fiber. But then you know by the Riemann-Roch theorem, for S, we know that the degree of L restricted to C times S is the Euler characteristic of this restriction minus 1 plus the genus of S. Okay. Okay, and this is how the definition. The degree along S is this. Okay, and similarly we define the degree along C. Finally, we define the most important thing, n of L as the negative Euler characteristic of our surface with coefficients in L plus the Euler characteristic along C. Sorry. Plus the Euler characteristic along C of L times the Euler characteristic along S of L. Okay, and once again, the Euler characteristic along C of L is the degree along C of L.
Что такое определение естественно?
Minus G
Что оно характеризует вообще?
Well, it is some, as we will see next time, it is some quadratic form on this Picard bar, on this quotient group. Okay, so let me maybe formulate the key theorem we'll prove next time. So first of all, this n is well defined on the quotient group. Second, it is always non-negative. And third, that it is zero only for trivial, so to say, only. Well, sorry. If and only if L it is zero. So in other words, L lies in Picard of C plus Picard of S. Okay, so on the quotient group, n is always positive. Well, away from zero is always positive. And next time we'll prove that n is quadratic. Well, we'll prove this theorem, but maybe theorem too. That n of L is quadratic. Okay. So maybe I have to stop now. And the proof will be given next time, but this proof will be not too short. It will take us the whole next time.
And could you please repeat why L is a flat?
Just because line bundle on the product. So certainly C times S is flat over C or over S, and any line bundle, any invertible sheaf is locally isomorphic to the structure sheaf, so it's flat as well.
I see. And you mentioned several times the notions of compactness during this lecture. However, you, as I remember, you said that compactness becomes trivial in the algebraic case, and we substituted.
Yeah, I was just speaking. I mean, projective. Compact curve is just a synonym for projective curve.
But like topologically speaking, as I understand, every affine curve is compact.
Absolutely. Everything is, yeah, quasi-compact.
Okay, so the proper.
It was just a figure of speech. I meant projective.
Okay.
So over complex numbers, it is compact in classical topology.
And is the projective and proper the same?
For curves, yes. In higher dimension, no, but for curves, yes. We proved this.
Okay. Thank you then.
Welcome.
Have you ever met with Mumford personally?
Me? Yes. Yes.
Hmm.
And
Like, what kind of person
pardon me?
is he?
Pardon me?
What kind of person is he?
Well, he's very, very smart. I mean, the speed he thinks is like at least 10 times faster than me.
Wow.
So
Thank
like
you.
lightning.
Thank you.
Welcome.
А можете, пожалуйста, еще раз повторить рассуждение, обосновывающее введение группы Пикара с чертой через первый класс с Черным? Почему нам потребовалось, ну, так важна какая-то билинейная положительно определенная
I
форма
didn't
в образе
explain
решетки?
anything. I didn't explain anything, and I don't plan to. Well, just in the complex analysis, or I don't know how to say, in color geometry, there is a very important notion of well, Hodge structures and some positivity. So there is a notion of primitive cohomology groups, and then certain scalar product on primitive groups is definite, say positive definite or negative definite. And this statement is called Hodge-Riemann bilinear relations. And if the underlying variety in complex case, the surface is the product of curves, then the Chern class map, the first Chern class map on Picard on Picard bar goes to this primitive part, and there this Hodge pairing is positive definite. So if you know some color geometry, then maybe it explains what we do from this point of view. But if you don't, never mind, we'll never use it. We just prove this positivity from scratch. But I just, if you have some experience in color geometry, then this positivity is nothing but the usual Hodge-Riemann bilinear relation.
Спасибо.
That's what I wanted to say. Sorry. Okay, so if there are no more questions, let me save the notes. Stop the recording.